Hi everyone, today we do section 4.2, homogeneous equation of nth order with constant coefficients. We are going to extend the theory we developed on second order equation on equation of any order. Of course, we are going to consider linear equations and with constant coefficients. So, typical linear equation with constant coefficients is going to look like this. A0, y, nth derivative plus a1 y n minus 1 derivative plus lots of other terms, and the last term is going to be an y equals 0. So equation is homogeneous. Homogeneous means that we do have right side equals to 0. We have constant coefficients a0, a1, a2, and finally an. All of them are constants. I'm going to write down a0, a1, an are constants. Well, as you probably remember, for second order equation, we were looking for a solution in the form of e to the power of rt and plugging in the function. We have a coefficient in front, but for right now, it's not very important. You know, if we substitute it with coefficient or without, it's still going to be equal to 0. So, which is producing characteristic equation. Well, before I do substitution to get characteristic equation, I want to develop a general nth derivative. So, first derivative of e to the power of rt is r e to the power of rt, right? Second derivative is going to be r square e to the power of rt. And nth derivative is going to be what? R to the power of n e to the power of rt. Well, I'm going to plug in all these derivatives into the equation. I'm going to take e to the power of rt outside of the parentheses just because it's going to be repeated everywhere, and I'm going to get my characteristic equation. So a0 by r to the power of n plus a1 by r to the power of n minus 1 plus lots of terms and an. There is no r here just because the function itself is just exponential function. E to the power of rt equals to 0. We do know that e to the power of rt is never equal to 0, greater than 0 always, right? So our characteristic equation is going to sit in this parenthesis, and we are going to turn it into 0, which is going to help us to find different r's which satisfy this this equation. And after we find different r's, we are going to get like different solutions, right? So normally, guys, this is equation of nth order, right? As you probably remember from algebra, nth order equation has n solutions. What are the options? Well, solutions can be real and unequal. We also can have what? Real equal solutions, repeated roots. And we also have complex conjugate solutions. Well, there is one more option here, which actually, because equation of nth order, we can have complex conjugates and they can be equal. So we can have repeated complex conjugates. So I'm going to point and put here in parentheses repeated. Okay, because I cannot squeeze everything here. So, well, just because more solutions, more different variations can happen, right? Well, generally speaking, the solution, the final solution is going to be the sum of all solutions with all these different r's, right? So C1 e to the power of r1t plus, and eventually it's going to be Cn e to the power of rnt. And for equal solutions, we have the strategy how to find actually different solutions, right? And C1 and Cn are going to be what? C1, C2, and Cn constant, which you define from initial conditions. We're going to consider example. It's very difficult to discuss a theory if we don't have any examples. So I'm going to start with example number 1. Example number 1, a third derivative of y plus 2 second derivative of y minus first derivative of y minus 2y equals to 0. I'm going to set up initial value problem. Y of 0 equals 0, y prime of 0 equals 0, y2 prime of 0 equals 1, right? Why do we have 3 initial conditions? Because equation of the third order, right? So I'm going to start with characteristic equation for r. We have r cubed for third derivative plus 2r squared minus r and minus 2 equals to 0. What I'm going to do, guys, I'm going to factor r squared from the first 2 terms and get r plus 2, and factor minus from the second 2 terms and get r plus 2, which is going to bring me to r squared minus 1. I'm factoring out now r plus 2 from both terms, right, and have r squared from the first term and minus 1 from the second equals to 0. So how many solutions we have? We have 3 solutions. Solution number 1 is going to be 1. Solution number 2 is going to be what? Minus 1. And solution number 3 is going to be 2. Oh, not 2, minus 2, sorry. Minus 2, right? These 2 solutions are solutions of equation r squared minus 1. So r squared equals 1. Maybe I should write it out. R squared equals 1, from where r equals plus minus 1. Sorry, for 2 everything is... Okay, now we are going to find the constant C1, C2, and C3. Let me kind of show you the equation. So we do have y of 0 according to initial conditions equals to 0. So I'm just plugging in y of 0 and I'm going to get 0 here is going to give me e to the power of 0 is 1, 0 here e to the power of 0 is 1, and e to the power of 0 is 1. So it's c1 plus c2 plus c3, right? Now derivative. Derivative at 0 equals to 0, 2 according to my solution, my initial conditions. Let me pull initial conditions. You see there are 0, 0, and 1. I'm sorry, I cannot put the whole thing at the same time here, so I'm going to keep it moving, but we already seen it, 0, 0, and 1. So the derivative here is just c1, right? I mean, exponential function, same. Here we are going to have minus because of this, and here we are going to have minus 2 c3. Y prime second derivative of 0 is equal to 1, and still c1, right? If we differentiate it one more time, minus t one more time, let me keep it over here, minus t one more time, we are going to get plus c2, and minus 2t one more time, we are going to have plus 4c3. So that's a system of equations we are going to solve. Let's just see. I'm thinking like how to simplify it to get something decent. Let's see. Yes, I think what I'm going to do, I'm going to add first and the second equation and get like 2c1, this cancels, and there is going to be just minus c3, right? I'm adding them, equals to 0, from where c3 equals 2c1. Now what I'm going to do, I think I'm going to calculate c2 now. I'm going to do same operation, but I'm going to subtract them, right? So let's say I subtract second equation from the first one. So c1 minus c1 is going to give me 0. c2 plus c2 is going to give me 2c2 plus, because minus and minus are going to give me plus. And c3 plus 2c3 is going to give me 3c3 equals to 0, from where I can write down that c2 equals minus 3c3 over 2. So now I can plug in C2 and C3. Well, I should solve it for C3 actually, right? And plug, well, I'm going to plug this like C1 equals C3 over 2 and plug in to the last equation with 1, right? 1 equals C1, which is C3 over 2. C2 equals minus 3C3 over 2 and plus 4C3, I think. That's what we have. Okay, multiplying everything by 2 is going to give me 2. And here I have C3 minus 3C3 is going to give me minus 2C3 and plus 8 plus 6C3, from where C3 equals 1 over 3. And plugging it over here back, C1 equals 1 over 6, and C2 equals minus 1 over 2, I guess. Let me just 1 over 3 here, 3 cancels, and 1 over 2, negative 1 over 2. Okay, so I think I calculated everything. I just need to probably write down the final solution. So y of t equals, my C1 is 1 over 6, so it's 1 over 6 e to the power of t. C2 is negative 1 half negative 1 over 2 e to the power of negative 2, and C3 is 1 over 3. Well, I'm not sure that this solution is correct. I'm going to double check it, but it looks good to me. I mean, if you see any mistakes, let me know and I'll fix them. So that's how we solve a real unequal roots. So basically, that's the simplest case. You find all different roots, write down as many exponents as you need depending on the equation, and find the constant from initial conditions, right? Now maybe we should consider something a little bit more complicated, like repeated roots. Repeated roots. Third derivative minus 3, second derivative plus 3, first derivative minus y equals to 0. Characteristic equation is going to be r cubed minus 3r squared plus 3r minus 1 equals to 0. Okay, we have perfect cube, which is going to be r minus 1 cube equals to 0, which is going to give me actually 3 roots equals to 1. So r, 1, 2, and 3 are equal to 1. Now remember how we were dealing with repeated roots before. We were just multiplying by t, right? So general solution is going to be c1 e to the power of t plus c2t e to the power of t and plus c3. Here we are going to multiply by one more t e to the power of t. And that's how we deal with repeated roots. I'm not going to solve initial value problems, that's just like a direction. And after that, if somebody gives you initial value problem, you calculate the constants, okay? More interesting situation is going to happen when we have complex roots. For complex roots, let's write down the equation. Y fourth derivative minus y equals to 0. From where characteristic equation r to the power of 4 minus 1 equals to 0. And we are going to have what? R squared minus 1, r squared plus 1 equals to 0. We do have two real roots, r1 and 2 are equal plus minus 1 from the first equation, right? And we do have two complex conjugate roots which are plus minus I. Well, how my solution is going to look? Two real roots, as usually, are going to give us two exponential solutions. Two complex roots. Here lambda equals to 0, mu equals to 1. are going to give us two trigonometric solutions. Because lambda equals to 0, there is no exponential factor. 3 is cosine of t plus c4 sine of t. Well, let me make sure that we are going to keep it straight. Okay, and same way we can find the constants, not very complicated. What if complex roots are repeated? Before we did not have it because second order equation can have only two complex roots and they cannot be repeated because they are going to be conjugates unless your equation is like complex coefficients. But here we can have complex repeated roots. Let me write it down. Complex repeated roots. Y fourth derivative plus 2y second derivative plus y equals 0. Characteristic equation r to the power of 4 plus 2r squared plus 1 equals to 0. This is a perfect square about r squared. So it's r squared plus 1 squared. It's just like imagine that you square r squared. It's r squared squared, it's r to the power of 4, and then 2r squared, and then 1. What we have over here, r1 and 2 are going to be plus minus I, right? If we bring this 1 to the right side, we are going to have plus minus I. But because it's squared, that's going to be also r3 and 4 are going to be also plus minus I repeated. So how do we work in this case? Well, first we write down like normal, like they are not repeated. So we are going to write down C1 cosine of t. Here lambda equals to 0, mu equals to 1, right? Plus C2 sine of t. And then because they are repeated, we are going to apply same technique we were using for repeated roots for real solutions. We are going to multiply it by t. So we are going to have C3t e cosine of t and C4t sine of t. Well, it's going to be hard to calculate all these constants considering that their products actually we differentiate them. But otherwise, that's how solution is going to look. Last thing I want to consider is when you have to extract several complex roots, more than like roots are not only conjugate, but you have to extract actually complex roots. Let me just show you example. Maybe I should move to a different page. Maybe a different page. Okay, I can make it straight. So, well, I think we considered example number 1, example number 2, number 3, number 4, and that's example number 5. So, what I mean by saying extraction of complex roots. Imagine that equation looks like this, y to the power of 4 plus y equals to 0, not the power of 4, derivative, fourth derivative. Characteristic equation of this one is going to be r to the power of 4 plus 1 equals 0, from where r equals the fourth root of -1. Well, in normal algebra, we do know that we don't extract roots out of negative numbers, but in complex algebra, we do know that fourth root of -1 is going to produce 4 complex roots. And they are going to be conjugates, but we'll need to kind of recall how do we calculate them. So I'm going to teach you a little bit how to do this because I'm not sure that everyone remembers. We do cover it in trigonometry, but trigonometry was a long time ago, before calculus 2, and before calculus 3. So let me review a little bit how to extract a complex root. How to extract an root. Step number 1, we need to represent it in a polar form. Or first, maybe should represent it as a complex number. Complex number here is minus 1 plus 0i, right? Because the number is real, we have minus 1 plus 0i. Step number 2, we'll need to convert it into polar form. Polar form is something like this. The r cosine of theta plus I sine of theta. How do we obtain this polar form? If you use a complex number plane where you graph a real part on x-axis and imaginary part on y-axis, any complex number, it's a pair of two numbers which can be treated as a y and x coordinates. For example, this number has x equals, the pair is actually -1, 0. If I graph it here, I'm going to have -1, 0. So the point sits over here. Polar form of the number consists out of the distance from the origin to the point, this distance. In our case, it equals to 1, right? And the angle from positive direction of x-axis, this is theta. In our case, is what? Is pi, right? So I'm going to write it down. So we have cosine of pi plus I sine of pi. So now, to extract a root of this number z, we're supposed to have n roots. I'm going to write down this number because you know that this number is not only like theta equals pi, but also theta equals pi plus 2 pi plus 4 pi. If you do several rotations, it's still going to bring you to correct point. I'm going to write down like this. Cosine of pi plus 2 pi n I sine of pi plus 2 pi n. Now, if you want to extract the fourth root of this z, you will need to extract the fourth root of r, and then you will need to consider divide this angle by 4. So it's going to be cosine theta plus 2 pi n, this 2 pi n, divided over 4, plus I sine of theta plus 2 pi n divided over 4. Well, this is going to produce 4 different roots. Let's see how. So, I don't know, let's kind of maybe write it down somewhere. Well, the fourth root of 1 is going to be just 1, right? So this is just a real number, a real root, like the principal value. But here we are going to have, I'm going to write down fourth root of z, number 0. When n is equal to 0, we are going to have just pi over 4. So we are going to have cosine of pi over 4 plus I sine of pi over 4, which is going to give us what? Cosine of pi over 4 is 1 over square root of 2 plus I 1 over square root of 2. Fourth root of z, number 1. And again, I'm numerating them 0, 1 because that's going to be number n, actually, what I substitute instead of number n. That's a cosine. If I substitute instead of n 1, I'm going to have 2 pi, and my theta is pi, so I'm going to have 3 pi over 4 plus I sine of 3 pi over 4. Well, 3 pi over 4, it's the same as pi over 4, but cosine in the second quadrant is going to be negative, right? So it's minus 1 over square root of 2 plus I 1 over square root of 2. Fourth root of z, number 2, well, n equals 2 is going to give me 2 by 2, 4 plus 1, 5. So it's cosine of 5 pi over 4 plus I sine of 5 pi over 4. Well, same square roots of 1 over square root of 2, but with minuses, the third quadrant. And the last one, multiplied by 3, 6 plus 1, 7, right? Cosine of 7 pi over 4 plus I sine of 7 pi over 4, which is going to give me 1 over square root of 2. Cosine in the fourth quadrant is positive, but sine is negative. And that's going to be all 4 different roots. Well, I would say it's a little bit like long to get all of them. But if you look at these 4 roots, you're going to see that we have 2 pairs of conjugates. Which 2 are conjugates? These 2 are conjugates. Remember that conjugate is A minus BI if Z is A plus BI. So this is plus, this is minus. And these 2 are also conjugates. You see? It's the same real part and like opposite complex part. So remember, these are just 2 complex numbers, right? And they are going to produce this lambda and mu. So each pair of conjugates is going to produce, the first pair of conjugates produce lambda equals 1 over square root of 2 and mu equals 1 over square root of 2. A second pair of conjugates produce lambda equals negative 1 over square root of 2 and mu equals 1 over square root of 2, right? Because this part is just like the number actually, not plus minus. Now we're going to write down our solution. Let me see if I shifted it too much. Right now our solution. So I'm going to start with this pair of conjugates. That's going to be e to the power of 1 over square root of 2t, and then c1 cosine of t over square root of 2 plus c2 sine of t over square root of 2 plus e to the power of negative t over square root of 2, the second part of conjugates, and c3 cosine of t over square root of 2 plus c4 sine of t over square root of 2. Well, I know it's kind of long to write it down, but this is the only way to do it. What are the rules for complex roots? Well, if you do have a real number here, you are going to have either real roots or conjugates. So it's not gonna like happen that you have just complex root without its conjugate, if you do have a real number here. If your number is even, I would say that, not always, but most likely you are going to have only complex conjugates. If your number is odd, you probably are going to have 1 real root or maybe 2. Okay? So that's how we deal with all different cases. And I think we can probably solve a problem. And I think maybe we will concentrate on general solution only. I don't want to look for constants. It's going to take too long. So self-work. Problem 1. In all 3 cases, I want you to find a general solution, okay? So y third derivative minus y second derivative minus y first derivative plus y equals 0. Case number 2, y third derivative plus y first derivative equals 0. And case number 3, y third derivative plus y equals 0. So we have 3 different cases. I want general solution in all 3 different cases. I'm going to count to 3 and then try to solve all these problems myself, okay? So 1, 2, 3. And let me push it all bit up, and I'm going to start with problem 1. So characteristic equation for problem 1, r cubed minus r squared minus r plus r equals to 0. Feels like I want to take r squared outside of the first pair and get 1 minus r. And I'm sorry, this is not r, that's just 1 actually. Minus r minus 1 here equals to 0. Little mistake, was not r, just 1. So I have r squared minus 1, r minus 1 equals to 0. So my roots from the first one, r1 equals 1, r2 equals minus 1 plus minus 1 as a square root, and the second one is going to give me one more root of 1. So we have two repeated roots. My general solution is going to look like this. C1 e to the power of t, C2t e to the power of t plus C3 e to the power of negative t. Okay? Okay, for the next problem, I think I'm going to keep, actually I'll need to show you at the same time the problem and kind of my solution. A second, let's see. Pages. So we're solving the second problem. Second problem is y third derivative minus plus y prime, right? Problem 2. Characteristic equation r cubed plus r equals to 0. Third derivative and the first derivative. From where taking r outside, I have r squared plus 1 equals to 0. Roots are r equals 0 and r equals plus minus I, right? R squared equals 1 means that r squared equals negative 1 actually, and plus minus I. So we have one real root and two conjugates. Y equals C1 e to the power of 0t plus C2 cosine of t plus C3 sine of t. I'm going to simplify it a little bit. 0t is going to be just 0, and e to the power of 0 is 1. So actually my first solution is just a constant. It has no exponential factor. Well, it can happen sometimes. Okay, and the last one, number 3, the third derivative plus function. The third derivative is still r cubed, right? And plus function, which is going to give me plus 1 equals 0. Here we are going to deal with extracting as cubic root, right? So r equals a cubic root of negative 1. Actually, it does not matter that you extract a cubic root of 1 or negative 1. It looks like cubic root of 1 is supposed to be equal to 1, right? And cubic root of negative 1 is negative 1. But we remember that cubic root is supposed to give us 3 cubic roots, actually. Why? Because if we have just 1, we won't be able to get 3 different solutions. And we need them, right? I'm going to extract a cubic root of 1. Well, negative 1 is still going to sit where? Negative 1 still sits over here. That's negative 1. Real part is negative 1. And the imaginary part is 0, right? So I'm still going to have negative 1 equals cosine of pi plus I sine of pi, which is going to give me cubic root of negative 1, 0 equals cosine of pi over 3, right? Denominator is like what you have as an index, I sine of pi over 3. Well, cosine of pi over 3 is what? 1 over 2. Sine of pi over 3 is square root of 3 over 2. Cubic root of negative 1, number 1. Let me move it a little bit up. Is cosine, and here we have 2 pi n. I'm going to add it over here, 2 pi n and 2 pi n. N equals 1, n equals 1, so we're going to have 2 pi plus pi, 3 pi. So it's 3 pi over 3, I sine of 3 pi over 3. Well, 3 pi over 3 is going to be cosine of pi plus I sine of pi, right? Cosine of pi is equal to negative 1, sine of pi is equal to 0. So we have negative 1. And that's negative 1, which we consider usually as a principal root here, right? When we extract in algebra cubic root of negative 1, we get this negative 1. And the last one is supposed to be conjugate of this. And I think I'm just going to do it, but if you're too lazy, you can skip it and just write down conjugate. There is no other escape for it. So what we have, 2 by 2, n equals 2, right? I'm going to write down n equals 0, n equals 1, n equals 2. n equals 2, it's 4 plus pi, it's 5, right? 5 pi over 3 plus I sine of 5 pi over 3. Well, 5 pi over 3 is sitting in the second quadrant, I think. No, that's sitting in the third quadrant. And we have minus minus 1 over 2 and minus I double check it. I, no, that's not minus, that's plus actually. A square root of 3 over 2, fourth quadrant. It's almost 6 pi over 3, sorry. Well, which is conjugate was this, right? As I said, it necessarily must be equal to a conjugate. So conjugates are producing actually this trigonometry solution, and the minus 1 is going to produce exponential solution. So y equals c1 e to the power of negative t plus, from these two conjugate solutions, lambda equals 1 over 2 and mu equals a square root of 3 over 2. So I'm going to write down c1 cosine of square root of 3 over 2t plus c2 sine square root of 3 over 2t and exponential factor 1 over 2t. You can put exponential factor in front. I don't know, like which way is more convenient. Yeah, we do solve all three problems. Well, again, that's just the solutions are going to be just combination of what we already learned from second order equations. Well, I think that's all for today. And sometimes I will ask you to find the constants, but if there are too many, maybe I'm not gonna ask you. Okay? Okay, that's all for today. Thank you.